The broadcast is now starting. All attendees are in listen-only mode.
Hi, everyone. Thank you for joining us for today's webinar on CEC 2018 and how the Sigma 3 relay is fully compliant. Some of you may know that this webinar is the last webinar of our 6-part series that has been happening over the past couple of months. If you're new to our webinars, all of the previous recordings and question and answer booklets are available on our website, so be sure to check those out. Prior to getting started, we have a brief but exciting announcement. Many of the questions and requests we've received from listeners are regarding how and why HRG is beneficial in their specific industry and many other application questions of this nature. With this being said, we have created a new webinar series that will begin in July. This new series will follow the same format of a live webinar with an opportunity to ask questions and then a Q&A document released the following week. As always, all of our webinars are free to attend and will be recorded. The requested and chosen topics are HRG for the healthcare sector, HRG for data centers, HRG for pulp and paper facilities, HRG for the petrochemical industry, and HRG for the food and beverage sector. So in the next couple of days, you can expect to receive an invitation to our new webinar series via email, and all the details will be provided, including registration links. Also, please feel free to share the invitation with all of your connections and or colleagues who you think would be interested in attending. Sometimes invitations can be filtered out into different email inboxes, so make sure to keep an eye on those locations as well. To stay connected with us during the break between the end of this series and the start of our new series, connect with the I-Gard LinkedIn page where we post relevant information and updates. With all of that being said, thanks for joining us for the final webinar of this series. Be sure to stay all the way to the end because we do have a webinar satisfaction survey where you can give us your input for our next series. I will now pass it off to Sergio.
Thank you, Jessica. Again, this is the final installation of the first part of our webinar series, and we've been having tremendous success with these things, which I don't know if that means these are really, really, really good, which I'm sure it does, or you guys are just really, really, really bored. But I hope you guys are all having fun and you're learning something and you're staying safe. So without further ado, let's start. Okay, that didn't work. All right, so just going over the Canadian Electrical Code, and this is a 10-300. This is different from where we were before with 10-1100 of previous electrical codes, and starts with obviously the qualified person. So where an electrical system is connected to an impedance grounding device, the system shall be maintained by a qualified person. Obviously that goes without saying, and I don't understand why it particularly pertains to this clause here, because I think all people that work on electrical systems should be qualified. And so I don't understand why special attention is needed here, other than that when you have a ground fault on an impedance grounding device, if you're going to measure the voltages in Z462 to recognize the state of de-energization, you're going to measure phase to phase and phase to ground. When you have phase to phase, you're going to get 600 volts A to B, B to C, C to A. When you measure phase to ground, you're going to get 600 volts on the two unfaulted phases and 0 volts on the third phase, or the faulted phase. So a qualified person should be able to recognize that that is a ground fault and not necessarily a blown fuse. If you had a blown fuse, you would probably have something like 347 volts to ground on the two of the phases and 0 volts to ground on the blown fuse phase. So I guess you have to make that determination, and a qualified person should be able to do that. So 10-302, ungrounded conductors of an impedance grounded system shall be insulated to the nominal line-to-line voltage of the system. This goes without saying. Up to 4160 volts, up to 5001 volts, the insulation on cables has to be 100%. There is no requirement to have cables at 173% when you have a fault that's on your system for greater than 1 hour. So you have to have conductors that are insulated to ground equivalent to phase. But that isn't normally an issue at 600 volts or anything below 5001 volts. It's only really a necessary requirement above 5001 volts. And if you want to maintain your ground fault on the system for greater than 1 hour. For greater than 1 minute, you only need 133% rated cable, but not many systems are going to be high resistance grounding above 5001 volts. What's new in 2018, however, is the integrity of an impedance grounding system shall be monitored, and the system shall have an audible or visual alarm that corresponds to the occurrence of A, a ground fault on the current carrying conductors, including the neutral conductor where line to neutral loads are served. This is relatively new because up until recently, in most jurisdictions, you're not allowed to have a high resistance grounded system when you have a distributed neutral. This is unique to Canada. And I don't necessarily believe it's a good idea to have a high resistance grounded system on a distributed neutral. And I can explain that a little bit later. A ground fault on the conductors connecting the impedance grounding device to the source has to be monitored, and a fault of continuity of the impedance grounding circuit from the system source through the impedance grounding device to ground. So basically what that means pictorially is we have to monitor if there's a ground fault on the neutral on a resistance grounded system when you have a distributed neutral. You don't have to monitor if there's a ground fault on your neutral if you have a solidly grounded system, which I think will probably cause more harm. And if you saw one of my previous seminars about the benefits of a high resistance grounded system over a solidly grounded system, you'll realize that if you had a ground fault on the neutral of a solidly grounded system, you actually defeat the ground fault protection system. So it is not a requirement on solidly grounded systems, but it is a requirement on impedance grounded systems. If you have a fault as well on any of the phase conductors, you have to monitor that. And that's relatively easy to do. The neutral is a little bit trickier to monitor, but it can be done. If you had a ground fault on the wire connecting the source voltage to the resistor, if you had a ground fault on this cable, it must be monitored. Now this is different than having a distributed neutral and a ground fault here. Because if you did not have a distributed neutral, you would still have to monitor a ground fault on the cable connecting the resistance, the ground fault protection on this cable over here. You also have to monitor if you have an open circuit in your resistor. But it goes a little bit further than that. It says a loss of continuity of the impedance grounding circuit from the system source. So you could have a ground fault or an open circuit here and here. If this was open circuited, you need to monitor that. Not only in the resistor, but you have to monitor it the complete length of this cable. Says the alarm required for subrule 2 shall be clearly marked, labeled as to its purpose, clearly enunciate the status of the system, continue signaling until the condition is corrected. on the occurrence of any of the conditions described in sub-rule 2, an impedance grounded system shall be automatically de-energized unless the following rules defined in sub-rule 5 apply. Where am I? So if the system is operating at 5 kV or less, the system serves no line to neutral loads, the ground fault is controlled at 10 amps or less, and the impedance grounding device is rated for continuous use. What's new in 2018 is a couple of things. One is you're allowed to have a high impedance grounded system with the distributed neutral. The other thing is you have to monitor the integrity of the resistor. So obviously, if you saw my previous webinars, having a system that's 5 kV or less and less than 10 amps is not only a good, effective arc flash mitigation system, it is very safe to do that, but you have to monitor the integrity of the resistor. You're not necessarily going to have a distributed neutral on every system. In fact, I would encourage you not to have a distributed neutral. According to the way the rules are set up right now, you could have a high resistance grounded system on a 120, 208 volt system, and I don't think that's a particularly good idea. But if you do have a system that's 600 volts and you limit the fault current to 10 amps, you have an arc flash mitigation technique, and you can keep the system continuously running, find where the fault is, which is ideal for pulp and paper facilities, hospitals, data centers, and these are coming up in our following webinars that Jessica mentioned at the onset of this webinar. But you have to monitor the integrity of the resistor and the cable connecting the transformer XO bushing to the resistor. So the way we do that, 10-304 basically has the same type of requirements, but for a low resistance grounded system. And for a low resistance grounded systems, where you have a resistor of not having a continuous rating, you have to de-energize without any intentional delay. The time rating of the device is coordinated with the time current rating of the protective system, and impedance grounding shall have an insulation voltage of at least equal to the system line to neutral voltage. So if you have a 4160 volt system and you have a 2400 volt 400 amp resistor on that system, then you can actually have a 6 ohm resistor, and we have to monitor whether that resistor becomes short or becomes open. That may be very difficult to do for some people, but we have found a way to actually make that work and detect that circuit. So we're going to discuss here why I believe a resistance grounded system having a distributed neutral is particularly unsafe. So when you have a normal system, A, B, and C phase are 347 degrees apart, 347 volts to ground and 120 degrees apart. When you have a fault on your system, all the voltages shift by 347 degrees, but more importantly, the neutral shifts by 347 degrees as well. So when you have a distributed neutral, I keep looking at the wrong screen. When you have a distributed neutral, and more often than not, your distributed neutral is going to have lighting loads on it, and your electrician, when changing the ballast on a 347 volt light, is going to lock out and tag out the switch that is takes the light out of service. He's going to measure the voltage phase to phase and phase to ground, determine that it is de-energized, lock it out, tag it out, start changing the ballast. But then what would happen is if you get a ground fault on C phase, anywhere in your facility, that neutral voltage can elevate to 347 volts above ground. And that poses a shock hazard. So that's why it's unsafe, I believe, to have a distributed neutral on a high impedance grounded system. So the voltages shift with respect to ground such that the unfaulted phases, A and B, are 600 volts above ground, and C phase is 0 volts, but more importantly, the neutral is going to be at 347 volts above ground, and we have not isolated it at this source or for this load. So part of the nuances of having this section in the code is that we have to monitor this cable. That means we have to look at things a little bit differently in order to have an installation that complies with the Canadian Electrical Code. We obviously cannot comply with the National Code if we have typically the way we've done things before is put a sensing resistor across the resistor so we monitor the integrity of the resistor. Unfortunately, we can't monitor whether this circuit is open or shorted if we're looking at this particular case. More importantly, we can't consider it shorted or opened. If that conductor becomes open, we have no way of knowing how it is. So what we've done is we've had to have a second wire going to the XO bushing of the transformer so that we can show continuity. So we're going to have a signal impressed upon the neutral. It's going to go up to the XO bushing and back down here. So we can monitor the integrity of this line, but we have to have two conductors going to the XO bushing of the resistor of the transformer to monitor the state of that conductor, whether it's open or shorted. Short is actually easy to do, but the open part is very difficult. And this comes from use of electricity in mines, which we've been doing for a long, long time. Part of the problem is that we have to monitor the integrity of that resistor when the power is off the system. When the transformer is de-energized, we still have to actively monitor the integrity of that path to ensure that the resistor is in the circuit before we're allowed to actually turn on the power. And this comes from M421, and we've been using this for a long time. However, we used to do it a different way. We had a DC voltage impressed upon the NGRS here, and we would measure the continuity of that path. Unfortunately, because we have a DC voltage impressed upon here, we couldn't tell if there was other issues. So if you had a short here, it would not monitor that. But M421 only required to monitor whether that resistor was in an open state, not necessarily in a shorted state. Now the problem is some transformers or generators are close coupled with a transformer, and you load the secondary of the transformer with the resistor, and it's difficult to monitor the integrity of the resistor. Is easy to monitor, but we can't monitor the line going to the neutral. So do we have to put two sensing resistors and sensing relays in here, one to monitor the line going to the neutral and one to monitor the resistor? What we've done in this particular case is we put another resistor here and call our neutral grounding resistor, and then had the transformer close coupled, because typically what you're going to do with this is you're going to have it for a high resistance grounding system. So the only time you want to have this close coupled is when you want to have pulsing. What my competitors say about this is that the combined cost of transformer and low voltage resistor is more than the cost of the resistor that is rated for a line to neutral load. In short, that's their way of saying they can't monitor the resistor and the neutral at the same time. A transformer saturated by ground fault through a rectifier can make the ground fault protection inoperative. Transformer inrush can be up to 12 times the rated current and can cause a voltage that is larger than expected. All these fancy words to say they don't know how to do it. The other thing they say is that where we've had issues, especially with the old way that we've had to monitor the integrity of the resistor, if there's YY connected PTs. If there is YY connected PTs, obviously injecting a DC current, and probably the problem is that there is such a low impedance, we can say that the path of the resistor is good even if the resistor is open, because the path, the DC impedance of this path is going to be very, very, very low. So using YY connected PTs with the old method of determining the integrity of the resistor and some of my competitors is not very good. So one competitor says the power circuit elements, other than the connected to the purpose of connecting a power system to a ground are often not compatible with these elements. Include single phase grounding transformers and grounded Y primary potential transformers. So one of my competitors cannot do this because they don't know how, and we do it a different way, so we can. So getting into the way we monitor the integrity of the resistor, there's two methods, active and passive. Let's discuss the passive way first. The difference between the two is active monitoring of the neutral grounding resistor means that when the system is de-energized and there's no voltage on the transformer, we can actively, as long as we have control power, we can actively monitor the integrity of that resistor and that path by injecting a signal onto the neutral and resistor through the NGRS and NGRX system that we have. Passive is we basically measure the voltage and measure the current that's on the system and determine whether the resistor is within tolerance or not. Some of my competitors change at 15% of the voltage or current. We transfer between active and passive at 5% of the voltage or current. So let's hopefully this will work now. So to give you an example, we normalize the voltage across the resistor through an NGRS, and we measure this voltage here. We also measure the current with our zero sequence CT. So as long as everything continues to operate when you have a ground fault on your system, the voltage and the current increase or decrease at the same rate, and they follow that green line. So at 100% voltage, 100% ground fault, you have 347 volts across that resistor, and you have 5 amps of current on a 600 volt 5 amp system. If you have a 50% fault, that's a 500% fault, 50% fault, you're going to have 174 volts and 2.5 amps. But the resistor is still rated for 69 ohms. So our limits when you have this type of a system in passive is we can monitor 70% of the resistance to 150% of the resistance. And for some of our relays, we can actually monitor 300% resistance. This line defines the 300% resistance change. And the reason we put that in there is because if you saw my presentation from I can't remember, neutral grounding devices with C57.32, sometimes we have resistor elements that are low resistance grounded systems that can have as much as 100% change in resistance over 10 seconds. And when you have 100% change in resistance, hold on. When you have 100% change in resistance and 50% change in current, you can have greater than 150% change in the resistance. So we would signify that that would be a resistor fault, even though it's a ground fault with steel that changes over the temperature range. So we've had to put in this 300% indication just to make sure that some of my competitors can still use our products. If, however, you wanted to use a 4160 volt system and a 400 amp resistor, I knew that wouldn't work. Our resistance is 6 ohms, and as long as you stay at 6 ohms, it's okay. But once you change this value, and the resistance changes, you can see that your normalized voltage and normalized current aren't following that green line anymore or outside this limits, and we signify that there's an alarm that way. When we actively determine the presence of the resistor or the integrity of the resistor, we have to monitor the line that's going from the NGRS or NGRX at this point to the XO bushing of the transformer or generator, and then back through the resistor. Sometimes we have two terminals here. One's called NN and one's called N. The reason we put that in there is to allow the user who's installing the gear to have two wires going to the XO bushing. And we have to have two wires because that's the only way you can monitor the open circuit of this line right here. We put two bushings in there, or two terminals. If the customer wanted to jumper those, they can. And the way this works is we put in a signal of a higher frequency. When we put in a signal of a higher frequency, we end up with a circuit that looks like this. We have the NGR here. We have the transformers, the inductance of the transformers here, which correspond to this, and the capacitive coupling of the phase conductors to ground. That basically comes to this type of scenario here, this equivalent circuit. So we have a resistor in parallel with an inductor in series with a capacitor. So when we inject a high frequency signal, we're going to get a lot of impedance on this due to the inductance, and this is frequency independent, so it stays constant. If we had a 6 ohm resistor here, we can have a 100 ohm resistor there. It's easy to detect whether when this 6 ohm resistor is open or shorted, because it's going to go either to 100 ohms or 0 ohms. Those are easy signals to detect. When you have YY connected PTs, same thing happens. Only now I've got the transformer here. We've got the PTs here connected to ground, and we've got the capacitive coupling of the charging current here. That equivalent circuit looks like this. Resistor, 2 inductors in series, and then that second inductor is in parallel with the capacitor, signifying the charging current of your system. So we can detect quickly if this resistor becomes open circuited, short circuited, and determine the integrity of that resistor and this line. And even if this resistor becomes shorted, we can monitor that neutral conductor shorts to ground, we can monitor that impedance, because that's going to be in parallel with this resistor right here. So we used to use a DC voltage and current injected upon the system. Now we're using a frequency dependent signal. So you can see that the resistor is not necessarily, doesn't change with the impedance or the frequency. It's frequency independent, shall we say. The inductance is going to increase the impedance as the frequency elevates, and the capacitance is going to decrease the impedance when you have a higher frequency. So because the capacitance is in series with the inductance, you're going to probably end up with a high level. So to show you how this works, if we look at the we're looking at this line here is the inductance of the transformer. This line here is the inductance of the transformer with all 3 coils in parallel. And we have the equivalent circuit that we're looking at and the resistive current. This works for a 6 ohm resistor, so 2400 volt, 400 amp, 10 seconds. If we change the impedance to my program became decoupled. If we change the impedance of the resistor to 0, we can quickly see that the equivalent circuit goes from 6 ohms to 0 ohms. Much like if we go from 6 ohms to 100 ohms, we can determine that right away because now we have a large step change. Now imagine you have a 6 ohm resistor as a neutral grounding resistor, and you have an open circuit. You're looking at the absence of 6 ohms in a resistive circuit. Basically, sometimes that's less than the tolerance of the resistors you're going to have in the sensing resistor, but because we can couple that with a frequency, we can see a significant change in that circuit. Now, we can detect frequencies, or we can detect resistances as low as 4 ohms. Whereas if we go to some of my competitors, without mentioning any names, their tolerance is basically 20 ohms, and they can't go up to anything above 100 amps. So the levels, the bracketed are basically limited temperature ranges. So it's from -40 to +70, it's going to change to 0 to 40 ohms. So you can see that we have a wide range of voltages and currents. We can monitor currents from 5 amps to 800 amps with 2 different devices. We have the Sigma 3 and the Sigma 3, I haven't come up with a name for that one yet, but I think right now it's called the Sigma 3 MD. So from 5 amps to 800 amps. Voltages, we can normalize the voltage using our sensing resistor from 480 volts all the way up to, well, we've gone as high as 36 kV, and I believe we're working on a 72 kV model right now. So the difference is how we comply is we put a potential on the system that has a higher frequency, and for really, really low resistance values, we change the frequency in order to observe the change in resistance. Going back to this type of circuit, we are able to detect whether that resistor is going to be open or shorted because we changed the value of the frequency. However, you still have the problem of determining whether the conductor going to the XO bushing is going to be open or shorted. So these types of systems are going to require more engineering on your part because you have, if to comply with the code, you need to monitor the integrity of this cable. You need to monitor the integrity of this cable as well as the resistor. YYPTs are not an issue anymore, not with our device. And I think that basically concludes how we monitor the integrity and comply with the Canadian Electrical Code. Oh, sorry, let me get to the. Jessica, are there any questions? I'm sorry that was a very short one this week, but it was. All I need to tell you is how we comply. And I apologize that my programs became disassociated with my Excel spreadsheet. Otherwise, this would look really nice.
Hi, Sergio. Yeah, we did get just a couple questions. So don't forget, everyone, if you do have any questions, feel free to go ahead and submit them. But to start off, one question that we received is, you mentioned a competitor can't detect when YY connected components are used. Can you explain more?
Well, no, I can't explain more why they can't do it, but I can show you where in their literature they say this. And I can't tell you which competitor it is, although you should be able to know if you've done this before. Well, basically what happens is, yeah, I can explain why it happens. It happens basically because they inject the potential with their relay here through a sensing resistor, and if you put in a DC source, you're going to measure a continuity path going here. So this path, even if the resistor was open, you're measuring continuity. So that's how they're able to be fooled that their system does not work, and that's what they put in their literature. Unfortunately, I can't tell you why, because that's their name right there. So it's a short name, if that's any help.
Thank
It
you.
has 3 numbers in it and 2 letters, but I can't say more than that.
Alrighty, next question. If the competitor is limited to 20 ohms, what typical NGR applications does this impact?
If you look at their chart, this chart came from their manual. So they're limited to 100 amps, according to this chart. So they have 2 types of sensing resistors. So they use one for less than 4,300 volts and one for greater than 4,300 volts. And you can see that their limitation is here, right? 100 amps up to 25 kV.
Okay. For HRG low voltage systems, the system needs to be de-energized on sensing resistor faults, correct?
No, it only needs to be de-energized if you have line to neutral loads. If you look at, can you repeat the question, please?
Yep, just give me one moment here to get back to it. For HRG LV system needs to be de-energized on sensing resistor faults. Is this correct?
No. On detection of a ground fault on an ungrounded conductor, the impedance grounded system shall be permitted to remain energized if you're operating at 5 kV or less, you serve no line to neutral loads, you limit the ground fault current to 10 amps or less, and the impedance grounding device is rated for continuous use. This is low voltage, right? Anything up to 600 volts. So if you have line to neutral loads, you must trip. If you limit the fault current to more than 10 amps, you must trip. If you're greater than 5 kV, you must trip. If you have a resistor that's rated for 10 seconds, 60 seconds, extended duty, you must trip. But if you comply with 5 kV or less, you have no line to neutral loads, or you don't have a distributed neutral, 10 amps or less, and you have a continuous rated resistor, you don't have to trip. Does that answer the question?
I think so.
Was there a second part to that question?
Nope, that was it.
Okay.
But if you did ask that question and you need any more clarification, feel free to submit another one. In the meantime, Sergio, this asker says that they missed the previous sessions, but they're wondering if we have equivalent devices for NEC in the US.
This is not a requirement for NEC, so you don't need to monitor the integrity of the resistor unless you're in the mining industry. So we can use this relay to monitor ground faults in the US, and you can switch off the resistor monitoring aspect of it.
Okay. Can the Sigma 3 relay successfully monitor health and continuity of the NGR circuit where a reactor is used, not a resistor?
I've never tried it with the reactor because if we're injecting a frequency on the system, well, let me correct this. In passive mode, yes, we can monitor the integrity of the reactor in passive mode. Where we have an issue is in active mode. If we're putting a inductor, where is it? If we're putting an inductor here, now we have an inductor in parallel with an inductor. So in active mode, it might be difficult. If these two inductances are somewhat similar, we're going to end up with half of the inductance here. So it's a little trickier to do that because the impedance of the neutral grounding reactor is frequency dependent. And it depends on the variation of the impedance of the transformer coils and the neutral grounding reactor. If there's a wide gap between them, yes, we can do it in active mode. I have never tried it.
Okay. What questions?
But again, in passive mode, it can be done.
Alrighty. Next question. What accessories do you need for the use of the Sigma 3 relay?
We need the Sigma 3 relay, the zero sequence CT, an NGRS normalizing resistor, and this is just, the resistance here is going to change with, you guys can't see that. Sorry, I'm pointing to things and you can't see it. The Sigma relay, zero sequence CT, you need the NGRS to normalize the voltage and use this in passive mode. There's also an NGRX, and we're making the determination of whether to make that one package or two packages, but the NGRX is used to inject the signal onto the system and measure the integrity of the resistor. So NGRS, NGRX, or NGR, this is where we're, Jessica, you need to help me now. We're either going with SX or XS, and that's a marketing tool.
SX, I like SX better.
Okay. The sensing CT, which we have the T9A, 6A, 9AS, 3A, 2A, and the Sigma 3. That's it.
Okay. What are the settings for the protective relay of a NGR rated 200 amps for 10 seconds?
What are the...
Do you want me to repeat the question?
Yes, please.
What are the settings for the protective relay of a NGR rated 200 amps for 10 seconds?
I assume the resistor is going to be rated for 10 seconds because it's a 200 amp, so it's probably not a continuously rated resistor. The maximum pickup level of the Sigma relay is going to be 50%. If you have greater than a 50% fault, we're going to trip. And so the let-through current is going to be set for 200 amps, and you can trip that resistor from 5 to 50% of that. And then you don't have to have any setting for the NGR, for the resistor monitoring, because in passive mode, we can pick up if that resistor changes greater than 70% or 150% of the rated value. In active mode, depends on the voltage.
Okay. Could you please show again how I-Gard detects in systems using the YY connected components?
Sure. Okay, so here's the YY connected PTs. You can see that the way we used to do things, you had a signal being impressed upon here, and you can fool the relay here to think that there was a continuous path. However, now that you have the NGRX and we're basically measure the resistor. So you have a 6 ohm resistor here. You could basically have a 70 ohm resistor on the inductance and maybe a 60 ohm resistor on that inductance over here. And then you have the capacitance over here connecting to ground. That's going to be inherent in any system. So you have a 6 ohm resistor in parallel with, for the sake of argument, a 140 ohm inductance. If the resistor becomes open circuited, we're looking at 6 ohms equivalent circuit to 140 ohms equivalent circuit. So we can monitor that relatively quickly, because if that resistor is out of the circuit, we're only looking at the impedance of the 130 ohms here. If that becomes shorted, we're looking at 6 ohms equivalent circuit to 0 ohms equivalent circuit. And that's easy to detect as well, because we're going from 0 to, so we're actually exaggerating the change in that resistance, because we're going from a 6 ohm resistor in parallel with anything greater than that is going to be a 6 ohm resistor. A 6 ohm resistor in parallel with something that's smaller than 6 ohms is usually going to be smaller. So we can monitor a low resistance grounded system quite simply. When we get into a value that's smaller than 6 ohms, we utilize a second frequency to determine what that resistance is going to be or should be.
Okay.
So don't think of a potential pressed upon this. We have a frequency that's put on this, and we're measuring that impedance.
Alrighty. Next question. What would be an order of magnitude cost for an NGR monitoring system at medium voltage, sensing resistor and relay?
Order of magnitude from a low voltage? Minimal, because the only thing you have to change is the NGRS and NGRX. The relay is the same. The sensor is the same. The zero sequence sensor is the same. The relay is the same. The only thing that has to change is, well, obviously the resistor is going to have to change. The sensing resistor is going to have to change, and the NGRX is going to have to change, and they're minimal cost.
Okay. What if the NGR is coupled via a zigzag auto transformer?
You know, funny you should mention that. We've implemented a couple of those, and we've had issues with it, but we've worked around it, and we found a solution for that because unfortunately the zigzag transformer is very low impedance when it comes to zero sequence ETs or zero sequence currents. So we have had issues with that in the past, but we did find a solution that works well with that type of application. Good question. I'm sure that's one of the people that had the problem with it. So that's the beauty of this now, because we have a direct correlation with our customers, and they say they have an issue, we fix it right away.
Great, thank you. Next question. This person's wondering how you comply with CEC 2018 with a reactor grounded system. Is passive mode detection sufficient?
No, I would say that using a reactor with the current way that the code is written will not work, because you cannot detect an open or short circuit, well, an open circuit, or basically you can't detect this.
I think that the asker
there and open circuit there.
The asker also said that he wants to note that the reactor was specifically required by the LDC to reduce/mitigate TOV on the system. I'm not sure if that changes anything.
I understand why they use a reactor, but it doesn't comply with the electrical code, and that's unfortunate, because I don't think when they thought of putting the code in the system in the CEC, they considered reactors. Right now, I don't think they consider reactors, but unfortunately, reactors fall into that. I'm not sure. You can probably write to CSA and have them reconsider this for the next code revision, which is, well, probably 2021 is going to be too late to make any changes, but 2024. Because I think it is important. Anytime you put an impedance device, and a reactor is an impedance device, I don't know if it's going to, if this type of a device, protective relay, can monitor that. Again, we haven't tried it, and I guess I'm going to have to try it and make sure that it works. But I don't think my competition could do it.
Okay. Does removing the grounding on the primary side of the Y-connected PTS solve the NGR monitoring problem?
Does removing the grounding on the primary? So I think you mean for a Y connected transformer. There should be no issue applying a resistance grounded system to a Y connected transformer, as long as you ensure that the HO bushing and the XO bushing are totally isolated from each other. And we've had issues where there was a jumper, or basically the same bushing was the HO and XO bushing. And then you're subject to the primary of the grounding of the primary circuit, and that's definitely not a good thing to have.
Okay, I think we have time for one more question as we're approaching 3 o'clock. Are the active and passive modes, are active and passive modes configurable on site, or is there a default mode that the Sigma relay is automatically set to?
There's a default that the Sigma is automatically set to, and it depends on what the voltage is of the system.
Okay. For everyone who submitted questions and didn't get a chance to hear the answer to their question due to the time limit, we do have a question and answer document coming out next week, as always, so you can find all the answers there. And as said at the beginning of this presentation, for those of you who joined late, we do have a new webinar series coming out. It starts next month. It's going to be a little bit more industry specific, as well as answer many application questions. We do have a satisfaction survey at the end of this webinar, so if you could stay on until we end the webinar, we would appreciate that, and we'd love to hear your feedback on how we can improve for our next series. Sergio, is there anything else you'd like to say?
No, I'm good. I'm glad I got a month off now. I can actually get some work done.
Thanks for joining us for our last webinar, everyone. And like I said, stay tuned and keep an eye on possibly your junk email or anything like that, because sometimes emails get filtered out and we don't want you to miss our invitation. And with that, we will end the webinar. Thanks very much.